Okay, so to begin with our third topic of this chapter, let's start to refresh our memory a little bit about so-called insoluble salt. Remember in chapter 3 in our Gene Chem class, when we talk about the precipitation reaction, we said there are certain type of ionic compounds that do not dissolve in the water. We call them as insoluble salts. For example, if we mix a solution that contains silver with another solution with a sulfate, and boom, we'll see the silver sulfate coming out of the solution, which is we call the precipitation reaction. Well, after for almost a year of the chemistry education, especially through the last two chapters of equilibrium, we understand first equilibrium is plausible. That means the equilibrium going back and forth will occur automatically. Since it's occurred automatically, so for any salt, just like the soluble salt, it will dissolve and dissociate to a certain degree. For sodium chloride, it dissolves a lot, of course. But for silver sulfate, it's not going to be that much, so it's dissociate tiny a little bit. But nevertheless, we still see the dissociation occurs in this so-called insoluble salt. Since dissociation and dissolution occurs, so we can no longer call them as insoluble salt anymore. So that is why we put a question mark, because that statement needs to be corrected. So from this chapter on, we call any insoluble salt as a slightly soluble salt. Just how big the difference between the soluble salt and slightly soluble salt. So here are the examples: sodium chloride and the silver chloride. And for sodium chloride, so the solubility is 36 grams for 100 grams of water. For silver chloride, it is 1.9 times 10 to the negative 4th grams per 100 grams of water. If we convert them into the molarities, so we can see just how huge difference between these two salts. All right, so now we understand that there's equilibrium going on for a slightly insoluble salt back and forth. We can definitely write up the Kc for this equilibrium. I just want you guys to pay attention here. The subscripts for the concentration of silver sulfate is a solid. That indicates we are talking about heterogeneous equilibrium. Remember, at the heterogeneous equilibrium, any pure liquid or solid has the concentration of itself. So that means they're 1 molar. So with the 1 molar putting into this equation, it's 1 molar, so this term can cross out. So we only have 2 terms on the top left. And this is no longer Kc that we'll talk about, so this is going to be the Ksp, the solubility-product constant. Okay. So we make it as Kc very specific. You may wonder why I put a 2 in red as exponent of equilibrium concentration of silver. That's because, again, we have a stoichiometry or coefficients as the exponent of a mathematic expression of equilibrium constant again. We have seen that in chapter 15, and we haven't not seen that quite often in chapter 16. Now in chapter 17, we need to pay special attention to the coefficients as exponent for the Ksp. It is my personal experience to tell you, we sometimes just overlook how important it is for those coefficients as the exponent as well as the other role that I'm about to tell you for a mathematical problem on the Ksp. Okay, so that is the case of silver sulfate. So if we put up the generic salt, say this is formula MMYY, and it's a solid, it undergoes dissociation equilibrium, right? So the forward direction is dissociation equilibrium. So we call it dissociation equilibrium. And the KSP here is this expression. So equilibrium concentration of the cation multiplied by with the power of its coefficient multiplied by the equilibrium concentration of anion powered by y. Its coefficient of the anion. So that is definition of a KSP. Now let's look at the dissociation equilibrium of a magnesium fluoride, which is right here. Okay, so if we dissolve magnesium fluoride in the pure water, so this is a pure water. If we dissolve in the pure water, we find out the solubility of this salt is not that great. It's in the order of 10 to the negative fourth of its solubility. That means the moles per liter as its unit. It's not great, but we still see the solubility. But once we put this equation or this equilibrium into a solution of sodium fluoride, and we find out the solubility decreases dramatically. The reason why I say it's dramatically because if you look at the coordinates on the y-axis, so you realize it's not like in the multiples, it's in the logarithm. So 10 to the negative fourth, 10 to the negative fifth, 10 to the negative sixth, 10 to the negative seventh, 10 to the negative eighth. So the solubility of the salt decreased dramatically to the neighborhood of 10 to the negative eighth moles per liter. We are talking about the solubility has been decreased by the factor of 10,000. What's the difference here? The difference is we introduced more fluoride, introduced by adding sodium fluoride into the solution. From Le Chatelier's principle, we realize as we increase the concentration of the fluoride, we put stress on the product side, equilibrium will shift the direction to release such press, or the pressure or the stress, so equilibrium will shift to the left. What does that mean? It shifts to the left. It shifts to the left, that means it's no longer dissociated that much. So there's going to be more solid stayed undissociated, undissolved. So that means by introduction of fluoride, the solubility of a slightly soluble salt like magnesium fluoride will decrease in its solubility by the presence of the fluoride, which is we call it common ion. Why common ion? Because fluoride F- is the anion of the compound. So we call it a common ion. So this common ion is no longer the conjugate base or conjugate acid as we see it in the buffer solution, but still we see the ion as its constituent of the species that we are interested in. So you may wonder what happened if we change the concentration of magnesium. Sure, we're still going to see the decrease of the solubility of the magnesium fluoride, and so this is something that we're going to see that in our calculation problem, which is at the end of this lecture. The solubility can also be affected by the pH of the solution, especially in our example here, carbonate. Carbonate is what we called, according to the old naming system, basic anion. Why is the basic anion? Because carbonate can accept the one proton to form hydrogen carbonate. Still it's anion, right? So two anions, carbonate is more basic than hydrogen carbonate. So we call carbonate as a basic anion. Well, let me put it this way. Basic anion is 2- charged anion. So let's see what happened if we have a compound called calcium carbonate. Calcium carbonate is a calcitite. It is a very common mineral on Earth. Okay, so this calcium carbonate is something that we see a lot, like a marble, like a chalk. All of this has a calcium carbonate in it. The calcium carbonate can actually react with the carbon dioxide in the air, and the acidity, the hydronium of the solution, to make calcium bicarbonate or calcium hydrogen carbonate. I just want you guys to notice calcium hydrogen carbonate is a soluble ion. Okay? It's a soluble compound. So they will dissociate into the cations and anions. That definitely changes the solubility of the calcium carbonate, which is what we call the slightly soluble salt. And that has a very huge impact in geography as well as in our social life. In terms of geography, so this is a picture taken from a national park in New Mexico. It's called the Great Craven. Okay, it's Carlsbad Craven. So in this Carlsbad Craven, and if you go down to the underground, you start to see that the big cave has a lot of these things going on. Okay, so the thing that's going from the top down, top up is what we call stalagmite, and the thing that dripping the solution from the top while it precipitates into the solid here is what we call stalactite. So these are the evidence of calcium carbonate has been precipitated once the pH of the underground water has changed. So for example, the mineral around this cave becomes more basic. Once it becomes more basic, that means the concentration hydronium has been going down. According to the Le Chatelier's principle, in order to make up more hydronium, the equilibrium shifts to, you got it, left. So we start to see deposition of calcium carbonate that gives us this beautiful scenery in the cave. So this is a simple reaction that could cause in our geometry. And also in our real life, it gives an ugly impact. So I believe this is a statue of Benjamin Franklin in some city hall of Philadelphia. Over the years, as we developed more and more industry, so our rain become acidic, so we call it acid rain. Since it's acid rain, so it increases the concentration of hydronium and it makes calcium carbonate with the reaction of carbon dioxide to form calcium hydrogen carbonate dissolves away. So that gives us the ugly mark on this statue. All right, so I just want to use this two. One is the beauty, natural beauty. The other one is the ugliness of our social behavior, to show just how reaction can do things as such wonderful and such ugly. Well, let's go back to the chemistry. When we talk about the solubility of a slightly insoluble compound or an ionic compound salt, we prefer to use molarity as its unit. And one thing I'd like to remind you, and if you look at the definition of this molar solubility, it says at equilibrium. That means the solubility here is You got it in an equilibrium concentration, just like a pH. I'd like to point out that at this time, KSP is not a solubility. KSP can actually calculate it from the concentration of ions in a solution, which also means it can be calculated from the solubility of ions or of the compound in the solution. As we try to understand the solubility of the slightly ionic salt, this equilibrium problem, I would to have you guys to think of this phenomenon in two steps. First, it is the equilibrium between the solid and aqueous compound of the salt. So, as you can see, as for first step here, we only change the solid into the equilibrium. That is the most difficult part. It takes time, it takes a lot of effort to have some salt that dissolves in the water. So that is where we start to see the back and forth going on, which is we call equilibrium, of course. Once we have a certain amount of salt dissolving in the water become aqueous, it undergoes 100% of dissociation. The reason why I separated this in two steps is the second step actually has a certain support over the years. Okay. So for example, silver chloride. Once the silver chloride starts dissolving in the water, it is a strong electrolyte. When we say strong electrolyte, so that means for whatever the silver chloride dissolving in the water, it undergoes 100% of dissociation. The only problem that prevents silver chloride, this slightly soluble salt, to dissociate is its dissolution. How good the silver chloride can dissolve it in the water, which means from solid to aqueous. So here, again, I just want you guys to think about the solubility in two steps. Not only we can understand it in the chemical sense, and what is even more is we can understand it in mathematical sense. So for example, the solid is something that we do not consider when we deal with equilibrium for mathematics. However, solubility is different. So that means AQ. So once we have something in AQ, it has its concentration. In our case here, it's solubility. So if we have this salt dissolved in the water, this amount, we call it solubility. So this solubility is for the entire compound with that formula, MMYY. And after the dissociation takes place, we understand that it's a stoichiometry problem, right? Because 1 mole of this compound will generate M moles of cation and Y moles of anion. So that is why for the concentration of these ions, not only we see the solubility, we also see the coefficients of each ion as a multiple for their concentrations. That is another important thing I want you guys to understand. Because this coefficient here appears twice. First, it appears as the multiple of the solubility of the ion, and it also gonna appear as the exponent of this KSP expression. So as a reminder, these coefficients will appear twice in the mathematical expression of KSP, especially when we use the solubility of the compound. One as a multiple of solubility, and second would be the exponent of the term of concentration of ion. All right, so from all this discussion here, now we understand if we have any slightly soluble salt dissolved in the water with a solubility of S, its Ksp is equal to this format. Again, as a friendly reminder, the subscripts of M and Y here are used twice, not once, twice, for the mathematical expression of a Ksp. All right, so once we understand the relationship or mathematical relationship between Ksp and solubility, I'd like to clarify, okay, so which is more dominant than the other? Ksp is a constant. It's a function of temperature. It's there, okay? Whether we can measure or not, the Ksp is there for a certain slightly soluble salt. So Ksp can be measured by the solubility of the salt. On the other hand, solubility is determined by the Ksp. So solubility is not the one that determines Ksp, it is the otherwise. It's a reverse. Ksp determines solubility. And also solubilities can be affected by the other factors such as common ion effect, as we discussed before, and the pH effect on the carbonates, hydroxides, on and on and on. All right, now, for any equilibrium, as we discussed so far, there's always a reaction quotient. So the reaction quotient has exactly the same mathematical expression as K. The only difference is for Q, we use the initial concentration. For this dissociation equilibrium, we too have a Q. But the Q here is no longer called the reaction quotient. We call the ion product expression. Why can't we call reaction quotient for this dissociation equilibrium? Because this Q, QIP, ion product expression QIP, is a reaction quotient for precipitation reaction. Precipitation reaction, that means it is the reverse reaction of dissociation equation or reaction. So that is why we cannot say just Q. We put a QIP in there to let the people to understand this Q, although it serves the very similar purpose as we discussed for the other equilibriums, but it represents the reverse reaction, not the forward reaction. Okay, so now let's see if we put the QIP in the first place, followed by the Ksp. If we draw the arrow from small to the large, we find out the arrow goes to left. Goes to the left, that means equilibrium shifts to the left to generate more solid. So that is why it is said solution is supersaturated and the precipitation will occur. So that means there's too much of a concentration on these two ions, so it will make a precipitate. So I just want you guys to realize QIP is the reaction quotient of the reaction in the other direction, not forward, in the reverse. If a QIP equals to Ksp, we understand, okay, solutions are saturated and equilibrium takes place. If QIP is less than KSP, it is said that the solution is unsaturated and the precipitation will not occur. Why it is not occur for the precipitation reaction? Because if you draw the arrow from small to the large, the arrow points to the right. That means solid will dissociate. If a solid dissociate, meaning no precipitation. All right. As our last portion of this KSP business, so let's see some of the typical mathematical problems that involve the KSP and solubility. As far as I can think of, there are 4 different types of mathematical problems associated to this topic. So first, we ask to calculate KSP from an equilibrium concentration such as pH and solubility. So here I want you guys to pay special attention to equilibrium concentration. This includes pH and solubility. So pH, solubility are equilibrium concentrations. So next 2 steps actually are the procedures that we're going to take in order to solve the problem. So first, we're going to convert the solubility into the molarity of the ions. Here, remember, solubility is for a compound, it's for the salt. So we need to convert the solubility of salt into the molarity of ions. So that is why we need to watch the coefficients. So once we know the equilibrium concentration of ions, the rest is going to be easy. Just simply use the mathematical expression of KSP to solve it. Second type of calculation problem is in reverse. So say, if we know the KSP, we try to calculate the equilibrium concentrations or the solubility. Of course, that equilibrium concentration could be pH, for example, if the anion is hydroxide. We're going to see that. Not directly for this type of problem, but we're going to see that as an example of the other mathematical problem. All right, so in order to solve this problem, since we know the KSP, and this is equilibrium, all right, so simply put, we just use KSP to calculate the equilibrium concentration of the ions. So from the stoichiometry or the coefficients, we will know what the solubility is for this salt. The third type of calculation problem is about the common ion effect. So this is the only type of math problem for KSP where we're going to see the ice table problem. We're going to see the ice table set up. Why? Because, say, we have equilibrium concentration, right? And certain concentration of anion. Equilibrium concentration of anion is, yes, initial concentration. So we see initial concentration and equilibrium concentration both involved in the question, ice table problem. Okay. So that is why we set up ice table, and we solve for x using KSP expression. Okay. And then x could be the solubility of the salt or through some stoichiometry calculation. The last type of calculation problem is we try to use QIP to evaluate whether this reaction is going to generate a precipitation or not. All right, so here, as our last example problem of this chapter, I handpicked 5 different mathematical problems. Question A and B here are the same type. One is for the solubility, and the other one is for the pH. Okay, so we use the equilibrium concentration to calculate the KSP of this salt. Now, let's start off our first question. In our first question, okay, so we have a solubility of generic salt as its mole solubility. So that means only 0.0740 moles in 1 liter of the water. Question wants to know what the KSP of the salt is. So you may wonder what happened to the temperature. Temperature probably is just to make sure that the concentration doesn't change or KSP doesn't change. Remember, KSP is a function of temperature, like the rest of K equilibrium constant. Since question wants us to get the KSP from the solubility, so our strategy here is first we convert solubility into the molarity of the ions. For this type of calculation problem, I want you guys to break this dissociation equation or reaction into 2 steps. First, solid to the aqueous of this compound or the salt, and then it undergoes 100% dissociation of the ions. Why do we have to do this? Because once that we determine the solubility is for this ion, this compound, and the compound only. So once we know the concentration of this compound, we can use the stoichiometry to calculate the equilibrium concentration of the rest, the cations and anions. So what is the equilibrium concentration of cation? 1s or some other s with a multiple. So it's 1s. Why is 1s? Because there's a coefficient of 1 that's in front of the cation, so that's why we ignore it. However, for the anion, you got it, 3. So the concentration of anions is 3 times over of the solubility, because this is what the coefficient says, or stoichiometry determines. So as for the equilibrium concentration, we got a solubility, so this concentration of cation, and 3 times the solubility of the concentration of an anion. So KSP can be obtained, and I just want you guys to realize, all right, so here comes the coefficient, again, used as exponent of this mathematical expression of KSP. All right, so plug the number in. Remember, carefully, we see 3 twice, right? As a multiple as well as exponent. And again, one last time. When we deal with KSP from the solubility, coefficients of the ions will be used not once, but twice. One as multiple of the solubility, one as coefficient of this equilibrium concentration as a part, exponent of this equilibrium concentration of ions as mathematical expression of KSP. In our second question, now we have a pH of the solution. Question wants us to figure out what KSP is. Remember, pH is an equilibrium concentration. So let's figure out the equilibrium concentration first. Since we know the pH, so we can calculate the pOH by subtracting 10.49 from 14. So we have 3.51. Okay, so take the 10 to the negative pOH. So what we have here is 3.1 times 10 to the negative 4th molar as equilibrium concentration of hydroxide. Where is the hydroxide in our equilibrium? So here comes the formula and equation. So we have this slightly soluble salt dissociate into the cation and hydroxide. So that is why we have hydroxide, and it can be measured by the pH. At the equilibrium concentration, we understand solid does not include in the calculation of KSP. And if we put X as the concentration of metal, hydroxide according to the coefficient of 2. So here it's going to be 2x. And we have just obtained the equilibrium concentration of hydroxide right here, 3.1 times 10 to the negative fourth. So 2x equals to 3.1 times 10 to the negative fourth. We should be able to figure out what the x is. So KSP, that's going to be the half of 3.1 times 10 to the negative fourth as the equilibrium concentration of the cation times 3.1 times 10 to the fourth. Don't forget, here comes the exponent. Okay, square. So we have 1.5 times 10 to the negative 11. That's the KSP of this slightly insoluble hydroxide. All right, so the third question here is the reverse of our second question. So say now we know what the KSP of this hydroxide is. Question wants us to calculate what the solubility of the salt. Since it's hydroxide, it is also as well to calculate pH if it's necessary. So here it's just the solubility. All right, so we know the equilibrium concentration, or we don't, but we do know the KSP. So what we ask to calculate the equilibrium concentration. So that's simple, right? So we have this reaction going on in 2 steps. We put the solubility under the aqueous hydroxide, soluble hydroxide, and the equilibrium concentration now, according to stoichiometry, that are going to be x for the metal, 2x for the hydroxide, because again, here's a coefficient. So that's what the stoichiometry is. According to the KSP based on the solubility, so we understand that we see the coefficients not once but twice. So 1 powered by 1, 2 powered by 2. All right, so the KSP here is 5.84 times 10 to the negative 16. So x times 2x squared is equal to 4x cubed. Okay, so be careful about the math if you want to get the full credit. Math is not difficult, but this is a very easy to get something wrong. So people usually forget that we have to take the square of 2 to make it 4 to make it mathematically correct. All right, divided by 4 on both sides, then take the cubic root. So x is equal to 5.27 times 10 to the negative 6 molar. And we understand x actually is what? The solubility right here. So solubility equals to 5.27 times 10 to the negative 6 molar. Well, so that is the end of the question. What happens if a question wants us to figure out the pH? So we calculate the equilibrium concentration of hydroxide, which is 2x, right? So 2 times this concentration. So we got a 1.05 maybe times 10 to the negative fifth. So that is the equilibrium concentration of hydroxide. And we take negative log, so we can have a pH, then we get a pH. If you have to go that far to get the pH of this solution. All right. As the fourth question that we picked in this example problem, question wants us to know whether the precipitation will take place if we want to mix 2 solutions. So the one solution contains 0.03 molar of the lead nitrate, and the other solution contains 0.020 molar of sodium bromide. And we're given KSP for this lead-2 bromide. All right, so we got the 2 salts. First is the lead nitrate, okay, or lead-2 nitrate, if you want to say it correctly. All right, so if we want to figure out the concentration of the lead, we need to look at what kind of salt of this lead-2 nitrate is. This is nitrate. We understand nitrate is a soluble salt. Since it's a soluble, we understand there's going to be a 100% dissociation, as we call strong electrolyte. So once the salt is in a solution, it will be gone completely. So according to stoichiometry, one formula unit gives 1 lead. So the concentration for lead is equal to 0.03 molar, same as that of lead to nitrate. As for nitrate, of course, it's going to be 0.060 molar, because one formula unit will provide 2 units of nitrates. All right, so that is the lead that we're interested. The bromide that we're interested in comes from sodium bromide, and we all know sodium bromide is a soluble salt. Again, any soluble salt is considered as a strong electrolyte leading 100% of dissociation. So the bromide must have the same concentration of sodium as a 0.020 molar. All right, so once we know the initial concentrations of these 2 ions, we can calculate the QIP of this PbBr2. Remember, it follows exactly the same mathematical formula as KSP, but for Q, we only use the initial concentration. Okay, so we put the initial concentrations in, but don't forget, okay, bromide, this concentration must be powered by 2. All right, so what we got here is 1.2 times 10 to the negative 5th. Compared to the KSP, which is a 6.6 times 10 to the negative 6th, so we understand the QP is greater than KSP. With the QP in the first place followed by KSP, we draw the arrow from small to the large. It's going reverse. It's going the other side, the solid side of the equilibrium. So that means, yes, we do see the precipitation. Last question. We are asked to calculate the molar solubility of magnesium fluoride, and now this time we introduce magnesium instead of fluoride. All right. As we already discussed, molar solubility is equilibrium concentration. 0.1 molar is initial concentration. So we have initial concentration, equilibrium concentration, both mentioned in this question. That is the problem of, you're right, Rice method or the ice table. So we set up ice table. As we set up ice table, we need to figure out the equilibrium concentration, right? So equilibrium concentration of ions. I'm sorry, I'd like to take it back. The initial concentration of certain ions. All right, so we have initial concentration of magnesium chloride. It's a soluble, of course. So if salt is soluble, strong electrolyte, 100% dissociation. So we have initial concentration of magnesium is the same as that of magnesium chloride according to stoichiometry, which is 0.10 molar. This is all we need because we have initial concentration for magnesium to present before the dissociation equilibrium takes place. All right, so this is the initial concentration we got. And of course, during the change, so we put X under the magnesium 2+. According to stoichiometry, so the change in concentration of fluoride must be 2x of it. So equilibrium concentration, so that would be 0.10 plus x and 2x for these ions. As for solid right here, so we don't have to care about anything that underneath because solid is not included in the mathematical calculation of KSP. So for KSP, according to this formula, and we plug x in there, so that is equal to 7.4 times 10 to the negative 11th. Again, anytime when we see there's a 500 rule, then we're going to check the 500 rules to see whether it's going to work. Because if it works, it makes the calculation a lot easier. So the initial concentration divided by the KSP, we find out the quotient is huge, right? So if the quotient is huge, that indicates compared to the initial concentration of 0.10, x is so small, we can actually ignore it. So once it's ignored, That is very simple calculation. So we can get x equals to 1.36 times 10 to the negative 6. I'm out of space right here. So if you can apply this back into a ballpark check of this KSP, you find out that that is exactly 7.4 times 10 to the negative 11. Well, what is the molar solubility of this salt then? According to the stoichiometry, we realize the coefficient of the salt and the coefficient of the cation is 1-to-1 ratio. Since the 1-to-1 ratio, so the molar solubility of the salt is the same as X itself. 1.36 times 10 to the negative 6 molar. This ends the entire chapter of 17. Okay, so in this chapter, we talk about a buffer solution. We talk about pH titration curve and slightly soluble salt. And the common of this number 1, number 3 topic that we can see here is common ion effect. And I'd like to point out for the common ion effect, sometimes we need to use ice table to solve the problem. For buffer solution, there's a shortcut, HH equation. If we want to use initial concentration instead of equilibrium ones, we need to make sure initial concentration divided by the Ka of this weak acid must be greater than 500. And of course, buffer solution has its own mathematical problems like addition of strong acid and base. Slightly soluble salt has its own mathematical problems like molar solubility, so on and so forth. So they have their own unique mathematical way to solve the problems. So this is something that I want you guys to pay special attention when you do those homework assignments. Okay, that's it for this chapter. Later on in this week, I might as well put up another video to show you just how we can analyze the various mathematical problems in this chapter 16 and 17 combined. Because chapter 16 and 17 are very closely related because they all based upon our concepts, our understanding of acid and base. Okay, so we need to know, okay, which one that requires ice table, which one does not require ice table. Even the ones that requires ice table, what is the unique approach for this particular type of math problem that we need to be aware. All right, so give me a couple more days and I'll put up this kind of lecture and I'll post it online when I get it done. All right, good luck. Have fun in finishing the next 2 homework assignments this week. I see you guys later.